All right, so this is example B. Integrate from negative infinity to infinity. 4 divided by 16 plus x squared dx. Okay, well, since both bounds are infinite, we're going to need to split this into two integrals. So we're going to go from negative infinity to anything you want. I'll pick 0, because why not? You can pick any number there. And then pick up again at 0 with the next integral. And go from 0 to infinity. So now the improper integral needs to be written as the limit of a proper integral. So since the lower bound is the one that is infinite, I'm going to make a go towards negative infinity and integrate excuse me, from a to 0, 4 over 16 plus x squared dx. Plus, and since this time the upper limit is the one that is not finite, I'm going to call it b, and have b go toward infinity. All right. So to integrate this one, I'm going to first of all think about that constant 4 and pull it out because I don't believe I need it inside the integral for anything. And then I'm thinking, is this one of my basic 20 definite integrals that, indefinite integrals, antiderivatives that I know, or is it not? And I believe it is. P 1 over 16 plus x squared dx. Okay. So this is the form of this is arctangent. So u is x, du is dx, so I don't need to introduce any constants, and a is 4. So this is the limit as a approaches negative infinity of 4 times 1 over a, so 1/4, inverse tangent or arctangent of u, which is x, over a, which is 4, and that will be evaluated from a to 0. And of course the other one is the same antiderivative. So I think I'll go ahead and look at the one on the left and simplify it and write what that would be, because of course the 1/4 times 4 gives us 1. So that's the simpler version of it that we would want to use. This will go from 0 to b. All right, so the next thing is to do the substitution. First, substitute in 0. 0 divided by 4 is simply 0, minus tangent inverse of a over 4. Right, plus the limit as b approaches positive infinity of, substitute b in first, and then substitute in 0. And of course 0 over 4 is just simply 0. Okay. So, tangent inverse of 0 is the angle that when you take the tangent of that angle, you get an answer of 0, and of course that is 0. So the tangent inverse of 0 both times it occurs is 0. All right, the big question is, as a goes to negative infinity, what does the tangent inverse of a negatively infinite, so because negative infinity over 4 is still negative infinity, what does that look like? Well, this is where your knowledge from pre-calculus will really come in handy, because you should know what the inverse tangent graph looks like. So if you'll recall, what happens is the x and y switch, and so it's better to write the scale on the x-axis in terms of 1s and the y-axis in terms of pi over 2. And if you'll recall, the inverse tangent graph has horizontal asymptotes at y equals pi over 2 and y equals negative pi over 2. And the inverse tangent graph looks like this. So, as we're taking tangent inverse of negative infinity, so to speak, as x goes to the left without bound, what is the graph approaching? Well, it's approaching negative pi over 2. So again, the tangent inverse of 0 was 0, so I'm ignoring that, minus the limit of tangent inverse of negative infinity, which is headed toward negative pi over 2. Okay, plus tangent inverse of infinity over 4 is basically as x increases without bound. So as x goes in this direction, what is the y value it's approaching? And of course that answer is pi over 2. And again, tangent inverse of 0 is simply 0. So our final answer is pi. All right. So let's move on to example C. All right. Oh, and by the way, one thing I forgot to say, because it didn't really have an effect on this problem, is that, remember I said something about look for discontinuities from now on. 16 plus x squared cannot ever equal 0 for any real number x, so it didn't have any internal discontinuities to concern ourselves with. I forgot to say that earlier, and it's something we need to think through at least. May not happen in every problem, but possibly could. Okay, so this function is cosine of pi x, and we know that the cosine function is continuous for all real numbers, so multiplying x by pi won't change that, it just changes the period. So it has no internal discontinuities. The reason this one is improper is because it has an infinite upper bound. So the first thing we're going to do is to change this into a limit of a proper integral. So I'm going to replace the infinity, because it's in the upper bound position, with b, and b will approach infinity. All right, so we now know, after having talked about this before, that the cosine of kx is something that we know how to do. So it is really just u substitution, but we figured out that we can do that a bit faster. Because we figured that out earlier, I'm going to say that that's 1 over k sine of kx is the antiderivative. Sine of pi x. So that goes from 0 to b. Now notice that limit, again, is just coming along for the ride. It's not actually being evaluated quite yet. We have to next do the substitution. So substitute in the upper bound first, so 1 over pi, sine of pi times b, minus 1 over pi, sine of, see, pi times 0 is 0, so that's going to be sine of 0. And the sine of 0 is 0, so that last term is actually going to just disappear because it turned into 0. As the graph of sine goes towards infinity, it's not going to change its look. It's going to continue to oscillate between the high value of 1 and the low value of negative 1 and every value in between, and it's never going to do anything different. And so there's not a particular single number real answer that sine heads toward as x goes to infinity on this graph. So pi times infinity is infinity, so sine of infinity doesn't approach anything, so that limit does not exist. Okay? It just flat doesn't exist. It's not infinity, it's not a number at all, it's not a numerical concept. The limit doesn't exist. And so what we conclude then about this problem is that this improper integral diverges. So if ever that limit doesn't exist, because it doesn't exist in this problem, for example, or if it approaches infinity or negative infinity, this will be our conclusion, that that improper integral diverges. Okay, now let's do D. Let me move this up a little bit so I have room to work. Okay, let's see, this is the integral from 0 to pi of x squared e to the opposite of x. So the very first thing we do is we write that improper integral. By the way, x squared and e to the negative x will never have you divide by 0 or anything weird like that, so no internal discontinuities to worry about. So the only issue here is that we have an infinite bound. So I'm going to replace that infinity upper bound with b and take the limit as b approaches infinity of that now definite integral from 0 to b. All right, so for this one, if I let u be something and dv be something, I'll pay attention to detail and choose my dv to be the exponential function e to the opposite of x dx, which leaves x squared to be my u. So du is 2x dx, and the antiderivative of e to the kx is 1 over k, so negative 1 over, 1 over negative 1 is negative 1, e to the negative x. Okay, so that means that this is the limit as b approaches infinity of uv, so negative x squared e to the opposite of x, uv, minus the integral of v du. The v has a negative, which I can pull out, making this plus. The du has a 2, which I'll pull out, making this 2, times the integral of x e to the opposite of x dx. And I forgot to write something. Do you know what it is? I forgot to say that this is now to be evaluated from 0 to b, and I also realized that I didn't write the bounds on this integral from 0 to b. So don't let those little details slip by. Okay, so I'm actually not going to start evaluating this quite yet, because in the end I'll evaluate all of it from 0 to b. So let's see, for this one, I'll change color so you can see this one's different. My choice for dv, is still e to the negative x, because it is an exponential function, and I paid attention to detail, which had me choose my dv as an exponential function. Okay, so that means that du is dx, and v, just like last time, is the opposite of e to the negative x. So this is going to be uv, so negative x e to the negative x technically, I guess I ought to write this. This is going to be from 0 to b, and this part will also be from 0 to b. Okay, that's uv minus the integral of v du. The negative in front of e to the negative x comes out in front, turning this into a positive. Integral of v du will be e to the negative x dx, evaluated from 0 to b. All right, so this will be negative x squared e to the negative x, then distributing the 2 through, that'll be minus 2x e to the negative x, And then the next antiderivative is negative e to the negative x. And all of that. Oops, I forgot to distribute the 2 to that as well. So let me go in and squeeze a 2 in here. Because this parenthesis right here in front of this 2 right there, that 2 has to be distributed throughout. Okay, so, and we'll evaluate that from 0, the whole thing from 0 to b. So, I'll move over a little bit so I have a bit more room. So what do I substitute in first? It's b. So this is going to be the opposite of b squared over e to the b minus 2b over e to the b minus 2 over e to the b. Notice that I dealt with that negative exponent in that way. So that's the substitution of b in for each x minus, now substitute 0 in for each x. That's going to be the opposite of 0 squared over e to the opposite of 0, which is 0, minus 2 times 0 over e to the opposite of 0. Oh, I'm sorry, to the 0, because I took down the denominator actually as 0. And I said that wrong in the first fraction there. Negative 0 squared over e to the positive 0, if you will, minus 2 over e to the 0. All right. So for the first term, the limit as b approaches infinity of negative b squared over e to the b. If I tried substitution, that would be negative infinity over infinity, which means this is a form for which we can use L'Hopital's rule, because that gives us negative infinity over infinity. So by L'Hopital's rule, that very first expression will be the derivative of the numerator, so negative 2b, over the derivative of the denominator, coolest function ever, is e to the b. Then 2b over e to the b, it will also be infinity over infinity, so I'm using L'Hopital's rule for it as well. The derivative of 2b is 2. The derivative of e to the b is e to the b. Notice what we're doing here is treating b as if it were variable x, because we're used to, f of x over g of x, but nevertheless. Anyway, now the next fraction, as b goes to infinity, that goes to 2 over infinity. Any constant over an infinitely large thing is headed towards 0. Okay. By substitution, 0 squared over e to the 0 is 0, minus 0, minus, what's that last thing? Yeah, it's 2, because e to the 0 is 1, and 2 divided by 1 is 1. So, sorry, it's 2. 2 divided by 1 is 2. Wow. Where'd that other answer come from? Okay, now the first term is still eligible for L'Hopital's rule, because negative 2b over e to the b will go towards infinity over infinity, or negative infinity over infinity. So by L'Hopital's rule, taking the derivative, that first thing will become negative 2 over derivative of e to the b would be e to the b, minus 2 over e to the infinitely large thing. 2 divided by an infinitely large thing is headed towards 0. And I have a bunch of minus zeros, so I'll just use 1. But be very careful. You then have to remember that that last thing is a positive 2. when you distribute the negative through. Okay, so the limit of the first item, -2 over an infinitely large thing, is going to head towards 0. Minus 0 plus 2 is 2. And so that's the value of that improper integral. And if you needed to say so, if someone asked you, does this converge or diverge, you would be able to say it converges. That wasn't part of the directions this time, so I'm not going to write that down. Just said to evaluate each integral. But do be aware that there are certain times that you might be asked a different kind of question. That is, does it converge or diverge, instead of evaluate the integral. So evaluate is what we did. The conclusion would be it converges, if that were the question. Okay, so the integral from 2 to 4. Okay, neither of those is infinite, so we are starting to feel really good about this one until we look at the integrand, and that's x times the square root of x squared minus 4 in the denominator. And any value of x that makes that division by 0 puts us in jeopardy. And so obviously if x is 0, the denominator would be 0, so we can't let that happen. We also can't let x be 2, because 2 squared is 4. 4 minus 4 is 0. Square root of 0 is 0. And so we'd be multiplying 2 by 0 and getting 0, which is no good. And we also can't let x equal -2 for the same reason as the last one. Now there are lots of discontinuities. If this integral went from, say, 7 to 12, none of those discontinuities would occur on the interval, and I wouldn't have to worry about them at all. I just ignore the discontinuities. So if there's a discontinuity at either endpoint or at an interior point, we have to deal with it. And the one that really matters here, of course, is 2, which is the lower bound of this problem. So it is something that we have to deal with. So we will rewrite that improper integral, improper because 2 is a discontinuity. Since that's in the lower bound position, I'm going to call it A, and A will be approaching 2 from which side? Well, since we're between 2 and 4, we're on the upper side of 2, so we'll be approaching 2 from the right of the definite integral from A to 4, which is not improper anymore. Let me see, that 2, I guess I could go ahead and pull that out right now. That's fine. Let me do that. 2. All right, so 1 over x square root of x squared minus 4. And is this integral one of our basic 20 integrals that we're supposed to know? The answer is yes, it is. So what is its antiderivative? Well, if you remember, this is where u is x, so obviously du is dx, which we have, no extra constants needed for this particular problem, and a is 2. And so the antiderivative of this one is 1 over a times arcsecant or secant inverse of, remember this one's kind of weird, it's the absolute value of u, so absolute value of x over a, which is 2, from a to 4. From a to 4. All right. So, the first number that we substitute in is the upper bound. Okay, so 2 times 1/2, of course, is 1. So this will be secant inverse of The absolute value of 4 is 4. 4 divided by 2 is 2. So secant inverse of 2 minus 1, because 2 times 1/2 is 1, secant inverse of the absolute value of A over 2. Okay, so secant inverse of 2 is a constant. We're looking for a secant of an angle whose answer is 2, and of course that answer is pi over 3. And the limit of the constant is the constant, so we can get that right away. And then we try the second one by substitution. This will be as A approaches 2, we can use substitution, and secant inverse of 2 over 2 will be 1. Secant inverse of 1 is 0. Yeah. And so this ends up being pi over 3. If those secant inverse values are things that you're having trouble remembering, please ask me about it during class time so that we can do any backwards thinking and try to get this back into your head from your pre-calculus days, because that is what that is about. It's a pre-calculus thing. Okay. Wait, what number was that one? I think that was E. Yeah, I'm sorry. It's about to do E again, which I don't want to do. You don't want to listen to it twice, I'm sure, so I can go to F like we're supposed to. Okay, 3 to infinity. Okay, I realize right now we have an upper bound that's infinite, but if you look at the integrand, it also has some discontinuities, just like the last one. In fact, it looks a whole lot like that last one, except for the constant here is 9 instead of 4. So the antiderivative is going to be a lot like what we just did, just, different number involved there. Now, what are the discontinuities of that function? Well, x can't be 0, x can't be 3, x can't be negative 3. In all those cases, we end up trying to divide by 0, and that's no good. The only one that impacts us this time is positive 3. And since that's a lower bound, we have to create a improper integral from, well, actually, let me back up and write this one more step in. So we're going to need to go from 3 to something. Why not 5? Because it doesn't matter, as you'll see in a minute. But pick a number between 3 and positive infinity, like 5 or whatever number you happen to like today, and make this a definite integral from 3 to 5. Of course, it's improper because its lower bound is a discontinuity. And then we'll pick up at 5 and go to infinity. And of course, this one's improper because one of its bounds is infinite. So these are two different types of improper integrals. Okay, so since it's improper, it needs to be rewritten as a limit as a letter like A approaches 3 from the right for the definite integral from A to 5, so it's now a proper integral. Plus the limit as B approaches infinity of the integral from 5 to B of our same integrand, 1 over x times the square root of x squared minus 9 dx. All right, now using what we did before, so I'm gonna speed this one up a little bit because we just did one like it. the antiderivative, actually for both of them, is the same thing. The antiderivative is going to be 1 over a, and what's a in this problem? 3, right? Because 9 is a squared. So 1 over a, secant inverse of the absolute value of x over a, which is 3. Okay? That'll go from a to 5. And this one will be the limit as b approaches infinity of the same antiderivative, 1/3 secant inverse of square root of x over 3, this time from 5 to b. So, we'll substitute into our antiderivative with 5 first. The absolute value of 5 is 5, so that'll be secant inverse of 5/3 minus, now we'll substitute into our antiderivative with a, and since a is between 3 and 5, it's positive, so I can simply say a over 3 because it doesn't really matter on that one. Because it's between 3 and 5, we know it's positive already. Then for the other one, it'll look very similar, but this one will have b approaching infinity. We'll put b in first this time. And by the same argument, since b is a number between 5 and positive infinity, it's definitely positive. Taking its absolute value is unnecessary. Minus, now substitute in the 5. Now, I want you to look at this and see if you can figure out why I said it doesn't matter where I stopped. I stopped at 5 and picked up again at 5, but I could have actually gone anywhere because no matter what number I picked, this is a constant and the limit of that constant will be the same constant plus a negative of this exact same thing, and the limit of that constant will be that constant. And so that part's going to add up to be 0. If it had been 7, it would have been 7/3 in both places for the argument of secant inverse, and they would have been identical. So as it turns out, it just didn't matter what number I picked. So those two cancel out and they become 0. So I'm going to not talk about those anymore. Now, secant inverse as we go towards 1. Well, let's see. Since we're doing this first one where a is approaching 3 from the right, so by substitution, 3 over 3 would be 1. Secant inverse of 1 is 0. Negative 1/3 times 0 is what we get from the first one. Then, plus, we're going to be looking at secant inverse of positive infinity over 3. Of course, positive infinity over 3 is infinitely large. So secant inverse of basically infinity. So this is another case where your pre-calculus really comes in handy, that you know what the secant inverse graph looks like. Say this is pi over 2 right here. So this is pi right there. And its graph has a horizontal asymptote at pi over 2. And this is 1, and that's negative 1. Then the secant inverse of 1 is 0, and then the graph looks like that. And at negative 1, secant inverse of negative 1 is pi, and then the graph goes like that. And so what we're thinking about is as x goes to bigger and bigger answers, because it's, remember, infinity over 3 is infinitely large, so x is going towards infinity. What is this graph headed toward? And the answer is, of course, it's headed toward pi over 2. And then recall the things I underlined add together to be 0, so that's why they're not represented down here at all. And so when you do the addition, oh, but I forgot to multiply by 1/3. Darn it. Let me back up. Remember, it's 1/3 times the secant inverse of infinity over 3, which we just decided was pi over 2. And so the final answer is pi over 6. There you go. All right, that is the last example for this section, so I will see you in class.